This is a problem calculating the force of gravitational attraction between two objects. And hypothetically, we have a 72 kilogram student here claiming to feel a noticeable force of attraction between herself and the Swanson Hall of Science that actually helps her go into the building, pulls her into the building when she walks near the doors. Let's go ahead and do a calculation using the laws of gravitation and some of the constants and the data that we're given here. We're going to assume the student has a mass of 72 kilograms and that the student is 25 meters away from the center of the building. The law of gravitation deals with spheres, one sphere attracting another sphere. So we're going to approximate here and just go to the center of the building, the center of the person, and the mass of Swanson Hall we're going to estimate 3 times 10 to the 6 kilograms. So that'll be our setup for data. We've made a little sketch of the situation. Let's go ahead and go into the calculation. So Newton's law of gravitation, we have a constant, capital G, the universal constant of gravitation. It was roughly measured 100 years after Newton came up with this law. 1798 in Cavendish, 6.674 times 10 to the minus 11 is the modern day value of this constant. And we have the two masses. We put their masses in kilograms. We divide by the distance between the centers of the two objects in meters. We know mass 1 is 72 kilograms for the student. We've been given that the mass of the building, 3 million kilograms, and we're given the distance between their centers, 25 meters. So you ought to pause the video here and take this data, put it into this calculation, and see if you come up with a number. Oh, assuming you've unpaused, now you're watching again. I came up with 2.31 times 10 to the minus 5 newtons. And again, I tend to give 3 significant figures for results for calculations. I keep more digits and intermediate values in the calculation, but round off here, and 2.31, 10 to the minus 5 newtons. 10 to the minus 5 newtons, that's not allowed. You may not be familiar with the Newton unit. Maybe you're more familiar with pounds. So let's convert newtons into pounds by applying the conversion factor, 0.225 pounds per 1 newton. So the newtons units will cancel. I'll be left with pounds. And we get 5.19 times 10 to the minus 6 pounds. And I'll just go to one significant figure here. We did a lot of estimating, the distance between the centers of the objects. The mass of this building is not known specifically, it's just a guess. So 5 times 10 to the minus 6 pounds, 5 millionths of a pound. I did look up on Google the weight of a mosquito. It's comparable. So talking about a mosquito, well, mosquitoes do not influence your path while you're walking. So it is not true that gravitational attraction pulls you into science buildings. I think the student just likes science. What about the person and Jupiter? What about the gravitational force between a person and Jupiter? Well, again, this law of gravitation laid out here, we need now to change 2 things, the mass of Jupiter instead of the mass of the building, and the distance from the person to Jupiter instead of the distance to the center of the building. So you can look this up, mass of Jupiter, the current day number, 1.898 times 10 to the 27th kilograms. That's a sizable increase from what we were using for the mass of the science building. But we also have a sizable increase in the distance. And in 2022, Jupiter was, the way the orbits work out, Earth's orbit's elliptical, Jupiter's orbit's elliptical, and at the time when Jupiter was opposite in the sky to the Sun, that's when we have our minimum distance from the Earth to Jupiter, and that number was roughly 5.9 times 10 to the 11th meters. I am ignoring that when we do this calculation, this number is from center of the Earth to center of Jupiter, but the person is standing on the surface of the Earth. I'm ignoring that difference. It's small compared to this number. Plug in the values and pause the video. You're back. You should have 2.62 times 10 to the minus 5 newtons on your calculator. And if we go back a page here, it was 2.3 times 10 to the minus 5 newtons between the person and a building. So 2.6 times 10 to the minus 5 newtons between a person and Jupiter. And I just might point out, sort of an aside here, there are some models of astrology that give credence to the gravitational force of the planets affecting your life. And I hope this little calculation disproves that for you. The mass of the hospital where you were born had a gravitational attraction on you when you went out the door that was greater than the pull of the planets. Jupiter's number here is sort of typical, bigger than the other planets' force of gravity on you. So astrology is not based on science. The force of gravity between you and objects on the Earth, buildings, and I only used a 4-story building. If you're in a large metropolitan city, the buildings are much larger and more massive, and the force of gravity between you and the tall building is greater. So here we have a calculation just showing you how we calculate the force of gravity using Newton's law of gravitation, and I hope you enjoyed that. There are other physics videos that I've recorded and put onto YouTube, and I have them listed in a grouped fashion, grouped by topic, and annotated: the title of the video, how many minutes long the video is, a description of what's being calculated, and also a direct link to the YouTube video. So you don't have to search for my videos on YouTube. You can just click on that link. You don't have to go to the playlist that I've put onto my channel on YouTube. All the content that I create here is free. You can't resell it, but it's free for you to use. I do not ask for your email address, your name, or any other information. And this website, gpclements.com, does not put cookies onto your computer. I hope you keep working sample problems and ask your instructor when you have questions.